So last time, we were looking at permutations, okay? And remember, with permutations, the idea is a permutation, it's a list, that's an ordered list, excuse me, where there is no replacement. Another way of saying that is if you have n possibilities for each item, okay? And you want to make a permutation of size r, meaning the permutation will have r items in it. So the list will be r units long, or it'll have r items, in other words. Again, this is without replacement, and order matters. Then the number of possible permutations is equal to this. N factorial over n minus r factorial. Again, I went over what factorial is last time. It's also denoted by P of n r. This is a little bit different than the notation they use in the textbook. The textbook notation I wasn't able to reproduce on a slide, a PowerPoint slide, so unfortunately, I couldn't use that notation, but I figured this one was okay to use. And if order matters, but replacement is allowed. Replacement basically means, without replacement means no repetition. With replacement means repetitions allowed. Then the total number of possibilities, again, this is order matters, but with replacement is n to the r. Again, you're making a list with r items in it. And for each item, there's n possible choices. Okay. So I just threw that in there. I'm not sure if the book mentions it. It's really not hard to see why. It's really just based on that basic counting rule that I went over before. That's really what it boils down to. So I really hope this makes sense. What I was going to go through was that kind of like that, that birthday problem the textbook does. I thought it'd be good to go through that. So basically here, let's say we're in a room. There's only 3 people in there, let's say. Okay? And we want to know their birthdays, let's say. So for instance, you would ask, the idea is that you're going to ask each person, when is your birthday? Not really so much the year, but the day, like June 8th, March 1st, whatever. We want to know how likely is it that each person will have a different day for their birthday. And here we'll also, just to make it simple, well, maybe simpler is a better word, we're assuming that there's 365 days in the year, and there's not more or less, like in a leap year or something, okay? And what I wrote on the slide, I hope you're reading it, it's really just illustrating that order does matter here. And that's what I'm trying to say here. So like if we ask the first person, they might say June 1st, let's say, okay? So for the second person, their birthday, we're hoping is not June 1st. For the event to happen where everyone has a birthday as a different day, the next person's birthday cannot be June 1st. It has to be something else. So order does matter. That's what I'm trying to illustrate over here. If the first person instead was April 8th, then the second person's birthday cannot be April 8th. So order does make a difference here. And that's really what I'm trying to show you here. So order matters. And hopefully what's obvious is you can't have repetition. You can't have we don't want 2 people with the same birthday, right? That's what we're looking for. So what does that tell us? That tells us we're going to have permutations here, right? We're looking for, from 3 people, we're looking for each person to have, what's the probability that each person will have their birthday on a different day from each other. Okay, I did email them to the notes again are in your inbox. But what I'm trying to show you here is we want to use permutations. And I just rewrote the problem here. So of course, when you're looking at probability, right, what we need to know how many possible outcomes are there for our event, which in this case is that all three people have different days for their birthday. And really what I was trying to show you there was order matters and repetition is not allowed. Thus, we get permutations. Right, there are 365 days in the year, so that's our N. R is 3, there's 3 people. The sample space is 365 cubed. I mean, you could think of the experiment as asking each people when their birthday is. And we're trying to see how likely it is that all 3 people have birthdays on different days. So our sample space is 365 cubed. That's what our sample space is. So again, the experiment is like we're asking each person when their birthday is. We're trying to figure out, well, how likely is it? What's the probability that all 3 people have different birthdays? So the favorable outcomes are essentially our permutations. And the sample space is this, 365 cubed. So, you divide these numbers. I did not calculate by hand. I used the calculator. I actually used Desmos's calculator. I think I've told you that before. They do have a function feature in there that allows you to do permutations. Basically, you end up with this. That's pretty high, isn't it? So that's pretty darn high. Okay, let me just do this. I want to make sure that made sense what I said. Okay, does this make sense? I mean, the birthday problem is, this is a very simplified version of it, but we'll get to the actual birthday problem. Okay. I mean, I really hope it does make sense. I know it's kind of a little tricky, I guess. Shouldn't be terrible, though. Okay, 2 people said yes. Everyone else. Oh, good, more people. All right. Well, let me keep going then. Oh, that's almost a no. Does anyone have any questions so far? All right. Well, let's keep going then. So that's what happens if we have 3 people. But now what we're going to do is kick it up a notch, so to say. Instead of 3 people, let's see what happens if we have 5 people. But it's really the same idea. The whole experiment is we're asking each people when their birthday is. Again, we don't care about the year. We just want to know what day. We're assuming there are 365 days in a year. I think if there's a leap year, there's either, I don't remember if there's 1 more or less. I think there's 1 more. I think February has like an extra day. But anyway, we're assuming there's 365 days in a year. Just to keep it simple, and we want to know, okay, what's the probability that all the 5 people will have different birthdays? What's the probability their birthday will fall on a different day? That's what we want to know. Okay, so our sample space, since we're asking, again, the experiment is we're asking each person when their birthday is. So our sample space is 365 to the 5th. For each person, there's 365 possibilities. So it's just the basic counting rule we're using here. Okay? And again, we want to know what's the probability they are all different. In other words, I mean, order, as I showed earlier, order does matter. Clearly, we can't have repetition. That's what we don't want to happen. So thus, we have permutations. I mean, you could think of it this way, I guess, if you really wanted to. There's 365 possibilities for the first person we ask. Okay, they're going to give us a date, and we go to the next person. And the next person, right, there's only 364 possibilities because we can't have repetition. We want all the days different. And then we go to the third person and so on. All together, we get this. Okay? And so our probability is this thing. And hopefully you can see the pattern now. You know, if you, let me go back to, for cubed, we have 3 and 3. Okay? For 5, this was 5, this was 5. What if we had 30 people in that room? If there are 30 people, right? Then what we would have to do, the probability would be this. I mean, just look at the pattern. You know, in mathematics, sometimes you have to look for patterns, you know, like what's really going on here. And we can see that for 3 people, we have a 3 and a 3. For 5, we had 5 here and here. You know, if the next slide, instead of 30, was 10 people, this would be 10 and this would be 10. And so for 30, we would get this. It's really the same kind of reasoning, except now you have 30 people. But now you can see that probability is pretty darn low. Now, is this the birthday problem? Well, not quite. Before I get to that fun probability, so to say, let me just stop the recording.